Floating point math is an approximation to real numbers, in other words, things beyond integers. Perhaps the most common floating point format is the IEEE 32-bit single precision floating point format, which is what we'll be discussing. That format takes 32 bits and arranges them as a 1-bit sign, so that's plus or minus, an 8-bit exponent, and a 23-bit mantissa. The value represented by a floating point number is the sign bit gives you a plus or minus, there's an implicit 1, a radix point, 1 dot mantissa value, times 2 to the power of exponent minus 127. Breaking it down, the sign is 0 is positive, 1 is negative. The exponent is not a 2's complement number, but rather is 127 bias radix 2. So what that means is you take the exponent, you subtract 127. Therefore, 2 to the 0 is an exponent value of 127. The mantissa has an implicit leading 1, so the value is always 1 dot mantissa value. The reason for this is that under normal circumstances, the floating point value is normalized so that the exponent is adjusted so that there's a 1 dot something, and there's no point spending a bit on a 1 that's always there. There are other special values we'll get to in a moment, but the first special value is that 0 is represented by all 0 bits. In floating point math, the general idea is that there's an exponent plus a mantissa representation. The 32-bit format we just discussed is quite common, but there's a 64-bit version that looks pretty much the same, follows the same rules, except the exponent and the mantissa have more bits in them. A significant issue with floating point math is that you can get round-off errors because there are only so many bits, and we'll see how that plays out in subsequent slides. Beyond 0, there are other special values. There's infinity, not a number, also called a nan, denormalized numbers that do not have the implicit 1 dot in front of the mantissa, and there's even a sign 0. We'll get to all those things. The antipatterns for floating point math include not accounting for round-off errors, which affects tests for floating point equality, not handling special values, and using floats if you really should have used an integer. Despite the fact that floating point numbers have this exponent that lets you represent big numbers, sometimes that's the wrong choice and you should be using an integer instead.